Thank you. Thank you to the organizers for the invitation to talk at this conference. I will start with a problem actually in group theory. So this problem was suggested by Vigold quite a long time ago, but is still open. And we take a finitely generated perfect group where finitely generated means that there is a finite number of elements in the group that can be used to talk about any other element of the group, and therefore every relevant map that is homomorphisms. And perfect means that the identity is the only commutative quotient of G. So in other words, G is equal to its commutator subgroup. Now, the question is G normally generated by a single element? What does this mean? If we take a subset of G, say X, any subset of G, we can consider its normal closure which is the smallest normal subgroup containing X. So it's the intersection of all normal subgroup of G containing X. If G is normally generated by a single element, it means that there is some element G whose normal closure is the entire group. So the question is this true? Can we find an element G in the group such that its normal closure, this is the notation for the normal closure of G often, is the entire group? Another way to think of that is that there is some special element that is not contained in any proper normal subgroup of G. This problem was told to me by Nicolas Monod a couple of years ago while we were working on other things. And he also explained to me that the question is about the finitely generated groups, because for finite groups, this is known to be true. And for groups that are not finitely generated, there are easy counterexamples, like, for instance, infinite direct sums of perfect groups would be a counterexample. And then we look at perfect groups, because if the group is not perfect, it's clear what it happens, because if it's not perfect, then the commutator subgroup is a proper normal subgroup. So every element that is contained in the commutator subgroup cannot normally generate because it would be in the commutator subgroup. And if an element is not in the commutator subgroup, what this means is that it maps non-trivially into the quotient, which is, which is an abelian group. It's called the abelianization of the group. And in abelian groups, every subgroup is normal. So the only way that this could normally generate if this group is cyclic. So this is clear. We focus on perfect groups where the question is not trivial. And actually, even if the problem has been open for a while, there is no answer. So it is believed the answer to be no. So people think that there are counterexamples, but a specific counterexample hasn't been found yet. So it might be one of those problems that are easy to state but difficult to solve. From the point of view of logic, one can ask a couple of questions. First, how logic could help solving this problem. Maybe it could come first. And two, possibly related to one, what happens if we consider the definable version of these problems? So what I mean by that is that we can consider the definable perfect groups in some structure or class of structures that we can choose. But instead of taking it finitely generated, we wanted definably finitely generated. And so looking at this problem from the point of view of model theory, and we need a specific notion of definable rank instead of normal rank. The rank of a group would be the number of this finite number of elements that we need to generate. We need a notion of definable rank. So we can choose several kinds of structure to look at. I want to focus on minimal structures for reasons that I will try to explain. So in general, whenever we have, say, a finite set, we can always define it in every structure just by saying that x is x1 or x is x2 or x is xn. And similarly, we can also always define cofinite sets by saying that x is not x1 and x is not x2 and x is not xn. So finite and cofinite sets are definable in every structure. And we call a structure minimal that could have any kind of language when these are the only definable sets in one variable. So if we take x in M definable, then it must be finite and or cofinite. Now, this seems a very restrictive notion, and in fact it is. However, there are many interesting examples, like for instance, any divisible abelian group or any algebraically closed fields. Any vector space of an infinite dimension, and so on. Now, whenever the structure has an order, in addition to finite and cofinite sets, we can also always define intervals. Because when we talk about definable sets, we are always allowing parameters. Before, we were allowing our finite set as parameters in our formula. So for intervals, the extreme of the interval can be used as a parameter. So the open interval AB can be defined by x bigger than A and x smaller than B. And we can also define intervals that have an infinite extreme by just saying x bigger than A, and then so these are open intervals. Then of course we can take a close, half close, because we have points and so on. So the corresponding notion, yes? Oh.
All good, please continue.
Okay. So a structure, whenever it's ordered, we call it O minimal. When every definable set subset of M is a finite union of open intervals and point. Sometimes you have it written just open intervals, because just the intervals when we assume that we can take them all kinds of intervals. So it's O minimal, it's the O stands for ordered minimal. So these are, of course, the minimal structure that have an order. Well, examples. First, we can just take the rationals with the order and any other dense linear order without endpoint. Then to the rational, we can also add addition. And with that, we can take any other ordered divisible abelian group. We cannot add the product. That's it's not minimal anymore. But if we can take the real numbers, then we can also add a product. And together with the real field, we can take any other real closed field. With real closed field for logicians are those ordered fields that are elementally equivalent to the real field. So those fields that have the same first order theory than the ordered field of the reals. But we have an algebraic axiomatization by saying that every positive element is a square, and every polynomial of odd degree has a root. We need infinitely many formulas for that, because we are quantifying over the coefficient of polynomials, but this can be done. Or still another way to think about it algebraically is that whenever we add the square root of -1, we get an algebraically closed field, exactly as it happens for the reals, that whenever we add the I, we get an algebraically closed field. So far, these examples are not really super surprising, because we know that all these structures have a quantifier elimination. But we can actually add a lot of other things to the reals without having quantifier elimination anymore, but getting on a minimal structure. The first example is the real exponential field. So where we add the exponential map. Now, this structure, I think Van der Dries gave an explicit formula that does not eliminate quantifier. So the structure does not have quantifier elimination. And actually, a minimal structure have been studied a lot at the beginning, just looking at this structure, because people wanted to understand the model theory of this structure, because there is an old question of Tarski, which is still open, which asks if this structure is decidable. So a lot of people have looked into this, and we don't know yet. It's possibly one of the biggest open problems in model theory. And but then by studying the model theory of this structure, in the end, Wilkie proved that it is a minimal. And moreover, later on, it was also proved that to RS, we can also add all analytic functions restricted to compact set. And this structure is called Rnx. So this is the real exponential field plus restricted analytic function. So we have a lot of interesting examples. And in fact, so while the structure at the beginning were introduced in a logic context to study ordered structures, it was very soon clear that these are very interesting beyond logic. First of all, it was soon clear that this is the setting where can be generalized real algebraic geometry. And there is a beautiful book of Lau van den Dries, which is called Time Topology and the Minimal Structure, that shows how this is done. And then more recently, an increasing number of applications are found also in other areas: number theory, algebraic geometry, complex analysis, and even outside mathematics, in neural networks, economics, and so on. So a lot of application. And even if the definition that we gave is about the definable set in only one free variable, there are consequences on all definable sets in every power of the structure. In particular, every definable set is a disjoint union of cells. So this is known as the cell decomposition theorem, that by looking at Van der Dries' approach, we fix a generic minimal structure and we need to define what cells are. In M, there are two kinds of cells. a cell could be a point or could be an open interval. And we attach to the cell a dimension. We say that a point has dimension 0, and we say that an open interval has dimension 1. And then by inductively, if we start with a cell in m to the power k of dimension n, then in m to the power k plus 1, we have again two possibilities. So let's say this is m to the power k, and we have our cell C. In m to the power k, then in m to the power k plus 1, we add the dimension here. We could have either the graph of a definable continuous function f. I said continuous because there is a topology here, which is the topology given by the order. And these cells, the graph of a definable continuous function, will have the same dimension as C. Or we can add 1 to the dimension by considering the region in between two definable continuous functions. Like an open interval, we can think it as the region strictly in between two cells of dimension 0. Then similarly here, and we add 1 to the dimension in this case. So these are the cells, and the theorem, the cell decomposition theorem, says that every definable set can be partitioned into finitely many cells. So it's a disjoint union of finitely many of these cells. Now, of course, this partition is never unique. So, well, with points is going to be unique, but in general, it's hardly unique. There are going to be infinitely many ways to find a cell decomposition of a definable set. However, there are two important invariants that do not depend on the partition, and one of them, it's the dimension that you may possibly guess is the maximal dimension of a cell in any cell decomposition of X. And the other invariant, which is called the minimal Euler characteristic, and it's denoted by EX, is the sum of the even dimensional cells minus the sum of the odd dimensional cells. Now, to convince ourselves that this is really invariant, I will take a nice example that Van den Dries does in its book, where we can take an open interval, I. This is a cell of dimension 1, so it's odd dimensional. By the definition, it must have a minimal Euler characteristic -1. If we take a different cell decomposition, it means that we are picking some points let's say A1, AK. And then the cell decomposition will be those K points and the K+1 intervals around them. So the minimal Euler characteristic of I will be the even dimensional cells are the points. So we have K points. The odd dimensional cells are the intervals, and we have K+1 interval. And this does not depend on K, it's always -1. So these two invariants are, of course, invariants definable by ejections, but also the converse is true in minimal expansions of real closed field. So this is a theorem. So whenever we take two definable sets, we can find a definable bijection between them, if and only if they have the same dimension and the same minimal Euler characteristic. Now, a couple of interesting properties of the Euler characteristic is that if we take a disjoint union, then the Euler characteristic is the sum. And if we take a direct product, a Cartesian product, the Euler characteristic is the product for any definable set. So if you notice, whenever we have a finite set, the Euler characteristic is the number of points, so it's the cardinality. And so for finite sets, cardinality and Euler characteristic are the same. And we have also, so this property is also typical of the cardinality of a set. And for groups in particular, when we study finite groups, we know that the cardinality plays a very important role, and there are a bunch of theorems that depend on the cardinality, like Lagrange theorem, Silos theorem, and so on. For definable groups in a minimal structure, one can use the minimal Euler characteristic to prove a good number of theorems, including Silos theorem, where the proofs are more or less the same, where we replace the cardinality with the minimal Euler characteristic. And so I'm talking about groups because in general, the study of definable groups is very common in model theory, and it is part of a general theme in mathematics of developing a theory of corresponding objects in each category. So for example, in the category of topological spaces, one studied topological groups. With the differentiable manifolds, one study Lie groups. With the algebraic varieties, we study algebraic groups, and so on. So for example, if we take the matrices 2 by 2 with the coefficient in the complex numbers, the invertible matrices, we can think of this as a definable set not only over the complex number, but over the real numbers by identifying C with R2. So this would be a definable subset of R to the power 8. And the operation of the group here is the matrix multiplication, which is polynomial in the entries. And because the complex number as a field itself is definable over the reals, we can define these whole groups first over the field of complex numbers and then in the field of real numbers. Now, I like more the field of real numbers because we were talking about before of a minimal structure, because we have an order and because this is in a minimal structure. And as I also said before, whenever we add the square root of -1 of a real closed field, we get an algebraically closed field. So, and the converse is true in the sense that whenever we start with an algebraically closed field, we can always find a maximal real closed field in it and complete it by adding the square root of -1, which gives us that every algebraic group, which is exactly a group like this G here, which is defined by polynomial equations over an algebraically closed field of characteristic 0, is definable in a minimal structure. So given this, we have that every algebraic group is definable in a minimal structure, and we can use the properties of the minimal structure to find out information about all algebraic groups. And one example is that, for instance, by using the cell decomposition theorem, one can prove that every definable set has finitely many definably connected components. So in algebraic group, if we take the connected component of the identity, and this is called G0, we can immediately conclude that this has finite index in an algebraic group. And so in this way, we have new information about the group using the fact that it's definable. But the information goes also in the other way. So we can find out properties of the structure by studying the definable groups on the structure. And one example is that whenever we can define a non-abelian bifinite group in a minimal structure, then we can use this group to actually prove that the structure defines a real closed field. So this is to say that there are several reasons why we are interested in studying the definable groups in various kinds of structure. In the particular case of Vigul's problem, I think it makes sense to look at it in minimal structures because we have a very nice property that we have the DCC on definable subgroups, which means that there are no infinite descending chains of definable subgroups, which allows us to define the definable rank. Because, so if you remember the problem we had at the beginning, we were looking at finitely generated group, but if we want to the definable version of this, we need to consider the smallest definable subgroup containing a set, but this may not exist. But in a minimal structure, it always does because of the properties. So we can then define the definable rank of a group, the minimal cardinality of a set, such that the smallest definable subgroup that contains the set is the entire group. And we call the group monogenic if the definable rank is at most 1. So while I was thinking about this definable version of the problem, then the first question was to look at which definable groups have finite definable rank. And I realized that all of them actually do have it whenever the structure has no countable interval. I will give an example of why this matters, which I was surprised by. So every definable group has actually a finite number of definable generators. And actually, we can find the bound using the dimension. So if the group is connected, so G is equal to G0, then the dimension gives already a bound. Otherwise, if it's not connected, we know that, as I was saying before, the quotient by G0 is always finite. So we can look at the rank of this as a finite group. And this is going to give us an upper bound for the definable rank. Thinking about it, actually, I should not have been surprised, because for algebraic group, this is known to be true. So the definable version for algebraic groups of this fact would be that there is a finite subset that is not included in any proper algebraic subgroup. And this is known to be true. And because every algebraic group is definable in a minimal structure, this theorem, actually, it's a generalization of this one. So we can think, and this is often the case, that in a minimal structure, one can generalize things that are true in both finite groups and algebraic groups, and also some kind of Lie groups. So it offers a setting where one can look at the different phenomenon in mathematics under a logic framework that try to explain it. So given that, given for minimal structures, this seems to be clear, then one can, yes, please.
No, sorry. That was an accident. Yeah, please continue.
Okay. Okay. Let me know if you have any questions.
Yep.
So one can then, of course, look also at other possible structure and theory, and think of if this is really special about minimal structures, or there are other structure theories where all definable groups have finite definable rank, or if not, if one can find a characterization of which definable group are definably finitely generated. Now, about this no countable interval thing, so the funny thing is that one can look at the same group in different structures, like, for instance, let's say we have any field. So I add also one to the language. And we can consider the group 0, 1 with the addition modulo 1. So which means that A plus B is going to be A plus B, the usual addition when it's smaller than 1, or A plus B minus 1 if A plus B is bigger than 1. Now, if we look at this group, one more familiar way to think about this is the unit circle, for instance, with the multiplication of complex number. If we look at over the reals, in fact, so if we look at over the reals, this group is monogenic because I can take 1 over square root of 2 and this generates the whole group because this is going to be dense. The subgroup generated by this, it's going to be dense in the circle. So the only possible definable set is going to be the whole circle. But if instead of the reals, I take the rationals, I cannot pick anymore 1 over square root of 2 as my generator. And whatever element I pick, it's going to be a torsion element, because if I add this guy m times, this is going to be n. So this is going to be 0. So this is a torsion group over the rational number. So it is not definably finitely generated. So n1 over q. So this is basically, this is the counterexample, because the point is it's for torsion groups that are not always finite that the things go wrong. So this is not definably finitely generated. So what also this tells us is that this notion of definable rank does not have a great model theoretic properties, in the sense that it depends very heavily on the structure. It does not depend only on the formula. So if we think about a definable set, usually we think about a definable set not really as a set, but as a formula that then gives us a function that maps into sets of the structures. So if we take an elementary extension, then what's going to happen to the definable rank is that it can get smaller. For instance, in this group here, it's not going to be a torsion group anymore. And so this is, so the definable rank, it's not going to be, it's going to be the same in general. So some more examples. So SO2 is just another fancy name for the same circle over the reals. So this is, as we were saying, is monogenic, and also the real numbers with addition is monogenic. And if we also take things that are not connected, it depends also a little bit on the part that it's not connected, because if we take Z2, for instance, which is a finite group that, let's say, it's going to be like the finite part G over G0, then this is cyclic group, so the rank is still going to be 1, because we just pick 1, and here whatever we like we can take. But if we take Z2 times Z2, now this is still dimension 1 as a group, but we have the non-connected part that then adds to the definable rank. Other two important examples of dimension 3 are SL2R and SO2R. So these are important because these are the only groups of dimension 3 that are not solvable in any minimal structures. So SL2R are the matrices of determinant 1. And this is, we can generate it just by using two matrices, and we have a lot of choice. We can pick any orthogonal matrix that it's not torsion, and any diagonal matrix, or the diagonal matrix can be replaced by any, this is called unipotent matrix with ones on the diagonal. And in general, is the trace that's going to tell us if it generates or not. So we need an element that are trace less than 2 and another one that has trace bigger or equal than 2. So this is the one that has trace less than 2, and these two have trace bigger or equal than 2. And the other, so this is compact. If you know what it means, it's not, doesn't matter. And this is, so this is not compact, and this is the compact one. And so SO3 is the orthogonal matrices 3 by 3 with determinant 1. And also this is generated by just two matrices, and we can just take so a nice thing about this example is that we can really pick the generators explicitly. Not only we know that there are two, we can choose them explicitly. And for SU3, we can pick every element that it's not torsion, and then any other element that it's not in the normalizer of the subgroup generated by G. And this is gonna generate. Okay, so this is the proof that I will not inflict all the details. So how much time do I have? Since we started late, I've lost track.
Okay, so we are delayed by 17, 18 minutes, something like that. So you should have, we're supposed to, okay, so until past, it should be fine.
Okay, cool. Thank you. But still, I will not inflict all details of this, but I will just tell you a couple of things. So this is the proof that the dimension of the group is an upper bound for the definable rank. We can use induction on the dimension of the group. The point where we use the fact that we cannot have countable intervals. So in the example, the problem of the example with Q here is that every element is a torsion element. So whenever we take finitely many, we can never exhaust the whole group because we will have always torsion which is of higher degree. And this is exactly the point of the proof that fails is for dimension 0 subgroups. We want to say that every element, if it's a torsion group, so if every element has finite order, then it's finite. And so this is why we need that the interval must be uncountable. Otherwise, this may fail. Besides that, so in the example we were looking at now, notice that SL2R has dimension 3 and we find two generators. Same way, SO3 has dimension 3 and we find two generators. Now, for dimension 1, of course, we will need to have one generator, but also for solvable groups, I can actually prove that whenever the group has torsion, then the rank doesn't reach the dimension. It's always less than the dimension. So this is something that I don't know if it's always true, but I think it might be true that the only case where the definable rank is equal to dimension is when the group is torsion free. But if the group is not torsion free, then the definable rank it's actually always less than the dimension. Okay, so we wanted to look at the groups that
what was that?
Sorry?
So, sorry, Annalisa, no, everything came down here. Can you go back, rewind 1 minute? Yes. Sorry.
Sure.
Yeah. Give us 1 second. We are just bringing down the screens again because the room sort of shut down somehow. That was strange. Give us just 1 second.
No problem.
Yeah, but we're getting you.
Wait, but this one? Why is that one not working? that solve completely this one?
I think we can continue and we can worry about this in the break, right?
All right.
One screen now.
All right, Annalisa, please. Is it visible for everyone? Just with one? Okay. Well, yeah. Annalisa, please continue. Yeah. Sorry.
Okay. So I was saying that I will still go back. I will go back to the original problem. The original problem is we want to look at the groups that are definable and finitely generated definably. So we look at the minimal structures and we find out that actually all of them are definably finitely generated, except whenever the structure has does not have a countable interval. So then the question is, if now we look at perfect groups, so groups that where the identity is the only abelian quotient, can we find one special single element that normally generated definably? So when I started looking at this problem, I wanted to look at this actually because I wanted to solve the original problem. So I wanted to find a counterexample. And what I was thinking is that if I'd found a counterexample in a definable way, I might understand what the idea, so what can go wrong for this not to happen. But then the fact is that there's no counterexample in minimal structures, and every definable set, which is perfect, is normally generated by only one element. So this was successful and failing at the same time in a way. So successful because one can prove the definable theorem for in the minimal case. So, and the theorem is that every definable perfect group G is normally monogenic. And what this means is that we can find an element G such that the normal closure definable of G is the whole group. And so this gives an answer positive in the minimal context to the definable problem. And the proof, so again, I will not tell you all the details, but the point is that one considers several cases, and the nice things about this proof is that one can find out a generator explicitly again by studying the structure of the groups. One can pick some smart element that one needs to prove that exist, but that basically in the first case, by looking at some torsion that it's unrelated, so by some coprime numbers. And then working on some definable and group stuff, one can explicitly find a generator. And so on the one hand, this is a positive solution in the minimal case. But then on the other one, if one wants to solve the original problem, this doesn't seem to be helping. But so my feeling is that the minimal structure are really special. So in some sense, the fact that one can generalize things that are known to be true, like for algebraic group and for finite groups, that's not entirely surprising. But then the problem that is open is to look at the other structures that are less nice and look at in which kind of structure every definable perfect group is normally monogenic, and then try to look at some counterexample. So look for a definable perfect group that is finitely generated from the definable point of view, but it is not normally monogenic, and I'm pretty sure this must exist. And possibly try to look at what ideas from that one can try then to transfer, let's say, to the original problem, to try to find the solutions to the original problem. So this is some homework if someone wants to try to do that. And so some reference for what I was talking about. So there is a preprint about this problem in the minimal case that needs to be updated. Actually, there are new things now, but so some discussion is there. And about the definable groups in a minimal structure. So this is a very lively field of research. There's a lot of people working on that. And what I suggest here are just 3 surveys, because the literature, it's very big. So a first survey of Margherita Otero that look at, and this is from 2008. So this was at the beginning of the study. Then Pillai's conjecture has also driven the study for a long time later on. And then finally, more recently, I tried to, starting from Margherita Otero survey and updated with the new result and the literature. And so you can find that in our webpage. And I think I will stop here. Thank you.
So much, Annalisa. Let me
Stop the recording 1 second.